Hello everyone, my name is Orang Wahid and I'll be talking about multi-body modeling, especially in a multi-domain simulation tool, and our focus will be MapleSim. The topics that I'm going to be discussing, all of these topics are at a high level, hoping to give you an idea of how the multi-domain system-level modeling tool that is MapleSim can bring multi-body modeling, 3D multi-body dynamic model together with other domains in one model to help the users explore their design and understand more about how they work. So we'll look at the multi-body modeling in MapleSim, some introductory slides about the library and its components. We then look at some multi-body models, and we discuss the different aspects that are presented in these models. Then expand the discussion to multi-domain type models that involve multi-body components as well. And then look at some more examples, and we discuss how these components come together. And at the end, I'll briefly talk about what is next, what is beyond modeling and simulation, as most of this webinar will talk about creating models and simulating them, but that's really not, that's just maybe less than half of this story. Okay. So multi-body models. A multi-body model in most tools will consist of a variety of different entities or components. In this case, we're talking about bodies, which encompass frames of reference, mass, inertia, and relative point of interest or point that interact with the environment for that mass and inertia. Rigid bodies, joints that provide connection between different bodies or to the ground and limit the number of degrees of freedom that they provide constraints. We'll have forces and motion as input to the system that the user can apply, and of course there are sensors to measure different things from the model, and visualization component to create a interesting and relevant playback of the dynamic simulation or the numerical integration. So forces. These are usually signal inputs that the user provides, and these signals together with the force components that or moment component that act on different bodies provide effects such as actuation, special components like a bushing or a rope, environment effect like gravitational forces, wind, or excitation such as a shaker that would exert force. The same in many models, there is one part of the dynamic system that has a defined motion specified for it, whether position, velocity, acceleration, or angular position or orientation, angular velocity or angular acceleration. Again, these are incorporated in many models, many multi-body models, for predefined motion, environmental effect, or other types of excitation. Sensors will then provide signal output, real numbers, values that the user can plot and also examine against known limits to evaluate the behavior of the model, on top of just looking at the way it moves. The signals coming out of sensors could be motion, as in rotational or translational, position, velocity, and acceleration, and also forces and moments. They can all be sensed. And the signal coming out of these sensors can then be used in some sort of a signal-based calculation to provide supposedly some sort of feedback for the system, like creating feedback control, we have a joint that rotates under the action of some force, and we measure its displacement, put it into a PID, and then close the loop to have a controlled actuation of some joint in our system. So this is like a basic model with some extra signal processing for the sensor outputs and also force and motions as input to the system. So in the context of MapleSim, MapleSim is a multi-domain environment. It's an acausal or physical modeling environment. It's the approach in MapleSim is based on blocks or components that you drag from the libraries to the screen and then connect them together. These components could be from a variety of domain, as we will see throughout this, the examples that I will present. And by connecting together the components, you create a valid system, and then the process of generating the equation for that system, manipulating those equations, and finally getting to a code that is then compiled and submitted to numerical integration. A variety of different libraries or sub-libraries exist in MapleSim, and we'll look at some of them. To name some of these libraries, we have signal blocks that basically all mathematical operations that you would do on the measurements that comes out of the sensors or any other source of motion or force. These are mathematical or arithmetic operations are done with the blocks and signal blocks. There's a library for electrical components, and this library includes analog components, multi-phase machines, and so on and so forth. There's a 1D mechanical library, and this library is divided into two sub-libraries, one for rotational components and one for 1D translational. We'll come back to this, as this is basically provides, there's a gateway from our multibody or the 3D multibody world to 1D world, which then gives us access to all the other domains. Of course, the multibody library, which we will look at a bit more in detail shortly. And there are other libraries like specific for hydraulic, thermal, magnetic, and battery, and a few others. In MapleSim, you cannot connect directly components from different domains together because these are specified by the type of ports each component has, and those ports are not compatible as they carry different variables, through and cross variables for an acausal connection. But between many of these domains, there are transformers that will convert one domain to another and then provide connection. Like an electrical motor provides a transform between the electrical domain and 1D rotational domain. So let's have a look at the multibody library. So the multibody library consists of 5 subgroups, similar to what I have shown in one of the previous slides. We have bodies and frames, forces and moments, which are the inputs to the system are defined here, and these forces and moment could be internal or external. Joints and motion, which includes both all the joints and also the specified or input motions to the system. A group of sensors for various different measurements, and a host of components for visualizing the multibody parts of your model. So the bodies and frame includes the fixed frame in space, a flexible beam component for incorporating flexibility in the model. The rigid body component encompasses the mass, inertia, tensors, initial conditions, everything that you would need to specify a rigid body in the system. The rigid body frames are connected to the rigid body and provide basically the points of interaction for a rigid body with the other rigid bodies. The force and moment section includes all the inputs, applied world force, applied world moment, and also relative applied force and moment between two bodies. There is a point-to-point force component that is called translational spring damper actuator. And also there is a bushing, which basically applies a reactive force of a spring-like effect and a damping-like effect between two frames, both in translation and rotation. There are a variety of different joints in the library and motions. We'll look at them. So we have two motion drivers, which you specify the relative displacement between two frames, either rotation or translation. These joints provide 0 degree of freedom as the two frames are completely defined with respect to each other. Then we have 1 degree of freedom components, which are the prismatic and revolute joints. There are 2 degree of freedom joints in MapleSim. One is cylindrical, one is the universal joint. There are 3 degree of freedom, like a planar, which provide 2 translation and 1 rotation. Spherical, which provides 3 rotation. And translational joint, which provides 3 translation but no rotation. And there is a 6 degree of freedom joint, which is basically a free motion, and it is only used when a relative initial condition is to be defined between two frames. So looking at the sensors, there are sensors for measuring Euler angles of a frame, absolute or relative position and rotation of a frame, or a frame with respect to another frame. And these sensors will give position, velocity, and acceleration. And also a separate sensor to measure the 3 components of the force and 3 components of the moment going through a section of the model. There are visualization components for boxes, cylinders, springs, and tapered cylinders, and also for bringing CAD geometry from a CAD environment into MapleSim to attach to parts that move. So these components, basically the examples that I'm going to be showing these are the actual visualization that will play out in the animations that I'm going to be showing. Okay. Let's look at our first model, and I'm going to limit the discussion of the details of these models, as the idea here is to give a sense of the type of models that one can put together with this acausal physical modeling environment. So here we have a simplified tracked vehicle, and it is this model. It's negotiating with a rough surface, and the track moves at a given velocity, as it is indicated by a signal as a speed input, and there's a steering input which changes the relative velocity between the two tracks, which causes a change in direction of motion. Looking at the main component, which is this subsystem here in MapleSim, you can go inside this subsystem by double-clicking on it. We'll see a number of other parts without going into too much detail here. There are signal components that come in, and these signal components are velocity and steering from outside, and these are calculated, or some numerical calculation are done on them to provide the portion of the velocity or the velocity value for the left track or the right track. And these components here, these 3 components, provide just visualization for the user. This components in the middle incorporates the mass and inertia for the body. And these 2 blocks here, inside them there are components for calculating the forces that the sections of the track and the uneven surface will develop, and those forces are carried through by this connection back to the rigid body, which is the track itself. So friction and contact forces are calculated in these blocks, which perform signal processing or calculate mathematical operation on signals, and then the result of that is applied to the body through a force and moment component. So this subsystem includes multi-body components as well as signal components. This is a kind of a fun example of looking at if we drop a ball on a bunch of pins, where would it end up? It's a kind of a good model to do a simple Monte Carlo analysis on the system, as the results or where the ball will end up is very sensitive to the initial condition of where the ball is released with respect to the first pin. So we can see here on the right we have the MapleSim model, which consist of blocks or subsystems. Then inside this subsystem we have multi-body components and force components. Sensors are used to measure the distance between the ball and each pin, and then mathematical equations are used to calculate the spring and damping force as a result of contact, and that is applied back to the ball. So one of the things that in an environment you can do, and this is just a simple example, is now that we have a model within our environment, it would be nice to be able to do batch type analysis on it. And here the plot that you see on the left hand side is a results of a Monte Carlo type analysis on the model, and we can see where the ball is likely to end up. Basically a bin around here, a bin on the other side, and in the middle. And these results are done through the connectivity between MapleSim, which is the physical modeling environment, and Maple, which is a symbolic numerical calculation tool that powers MapleSim. MapleSim sits on top, basically. And there are commands that you can run in Maple to access a MapleSim model. And for example, here you can see that we are just issuing a Monte Carlo command, which runs, in this case, 1,000 runs using multi-threading, and basically collects the data. And then the data is visualized using Maple. Again, a simple system that incorporates multi-body components and signal blocks. Another example is a Quadcopter. So this example involves a rigid body which represents the mass and inertia of the body of the quadcopter. As it's shown here, there are 4 propellers, and the speed of these are controlled via a controller to achieve a position and orientation in space. So this model incorporates the mechanical or multi-body parts that represent the dynamics of the system, and also a controller for it, which the same approach as we've seen in the previous example was done through the connectivity through a Maple environment, which is where you can manipulate equations and do a symbolic operation on the equations that define your MapleSim multi-domain model. And these steps can be done all symbolically and programmatically to get the definition for a controller. In this case, there's an LQR controller that is generated by getting the equations of the system, linearizing them, and then following the step to find the gains that would stabilize the system. So in this subsystem, we have rigid bodies, revolute joints, and forces that gets exerted to various points of the rigid body as a result of the rotation of these blades, and a nonlinear force relationship between the angular velocity of each rotor and the force that gets exerted to the body. And in this section, we have the controller, which basically uses the sensors value that come from the inertia measurement unit in the body, and then do a variety of numerical operation on them to get the feedback signals to then control the velocity of each motor. Another example here is a different domain or different application we are looking at. This is a 4-post shaker. Again, we have a multi-body part that, as you can see in this animation, incorporates the representation of tires, a representation of each of the 4 posts that get their input from a signal generator. There is a representation of the suspension system of the vehicle with linkages, joints, and springs and dampers, or the shock absorber for the each corner of the vehicle. And then the signal generator provides a sine sweep that changes its frequency, and they are applied to the 4 posts with a selected phase difference by the user, and then that will excite the system. This is a case of using motion or predefined motion inputs to not include the dynamics of the actuation system. Of course, one would do that, would be able to do that in MapleSim as well, as we will see in the second parts of the examples that I'm going to show, where we move away from just having models that incorporate multi-body components to models that expand and bringing other domains for a system level model. So if we look at the body, the vehicle body in the middle here, this is how the subsystem looks. You can identify the rigid bodies which incorporate the mass and inertia tensor for the main chassis, and also representing the unsprung mass that will move up and down with the posts. And there's a sensor for plotting the measured roll, pitch, yaw angles for the main chassis, and a visualization component to basically visualize how the vehicle orients in space. And if you look closely, you can see that the visualization is in the middle here as I rerun the animation. And if we look at any of these suspension subsystem, which is a double wishbone type subsystem, we go here and you can see we have revolute joints, and we have universal joints, and more subsystems that represent the mass and inertia and geometry of the upper A arm and the lower arm, and also another subsystem which inside it there are more rigid bodies and rigid body frames that represent the mass and inertia of the spindle part. Here we see one of those force components that we saw while we were reviewing the Multibody library, and this is a point-to-point force component, which in this case is used to represent the spring and damper forces for the suspension. And of course there are visualization component to visualize the damper and also the spring around it. Okay, so as we have seen in the brief look at the MapleSim multibody library, part of a multibody model is the joints. And there are a variety of different joints, and there are other joints that one can create by combining different combination of joints with few degrees of freedom and create more compound joints. But this is the list, a typical list of available joints in most multi-body simulation tools. As we have seen, we have the translational, planar, spherical, universal, cylindrical. The two that we are here we're gonna be focusing on, and it becomes apparent shortly, are the revolute and the prismatic joints. As I said, these two provide only 1 degree of freedom, and they are the two components that provide connection to the 1D mechanical domain. For the revolute, this can be connected to 1D rotational domain, and for prismatic, this can be connected to 1D translational domain. So here we have a gateway to incorporating drive lines, gears, in rotary inertia, stiffnesses and damping in the shafts, basically drivetrains, clutches. And for translational, you can have translational spring damper, loss element, friction, and variety of different things. Actuations could be done through these two domains depending on the type of system that you have. These two domains, through appropriate transformers, can be connected to electrical, hydraulic, magnetic, or thermal. We'll see some examples of electrical, hydraulics, and thermal in this presentation of how these domains connect together. So this is how the multi-body part of the system gets incorporated in a bigger system, the system level model that incorporates other domains. Let's look at some examples, but before that, just wanted to bring this point to an end, is that considering a multi-domain system, we just looked at the multi-body components and joints and visualization and some signal blocks. Then through the use of transformers, we can connect that to other domains, like we connect the revolute joint to a 1D mechanical, and then through a electric motor, we connect it to electrical domain. Or through a rotary to translation joint, like a gear pinion, we can connect rotary then to translation. Or go from prismatic to translation, and then through a piston, hydraulic piston, go to a hydraulic domain. So that's how your model gets connected and become bigger. In MapleSim, one of the things that the users can do is create their own physical components. And so by writing the equations of a representation of a physical components, they can add their own custom components for different physical domains that exist in MapleSim. Also, they can create their own domains that does not exist. So you can imagine combining different inputs and outputs and true and cross variables that represent a certain phenomena. You can create your own physical domain and then basically expand the model that way as well. Okay, let's look at our first multi-domain model. This is the Now robot. And so this model is a dynamic model of the actual robot that is created in MapleSim. It incorporates all the degrees of freedom and they are actuated. It incorporates the contact between feet and ground, and it can execute a predefined motion, as does the actual robot, and show the balance that it can achieve. And it could be platformed to do some interesting dynamic analysis of different types of motion. But what we are able to do in MapleSim is just go beyond having the dynamic of the system and the multi-body part. We can look at the more detailed or more subsystems in the same environment, all in one. So here we are looking at just one of the arms, focusing on one of the arms. We can see that there's a string of components that or subsystems that represent the joints, the inertias, and also actuations. So in this subsystem, we have multibody, we have 1D rotational. So this connection from here, from the servo actuator to the joint, is through a rotational, 1D rotational domain. We have signals, we have electrical domain, because all of these servos are electrical motors. And we have battery library, which is also connected to the electrical domain, but we have library of specifically for different types of batteries. So they all come together and they provide the forces that require the joints to execute or follow the designated predefined path. If you look at one of those servos, this is what we see inside them. In this case, the model even extends to incorporating some thermal effect. So the heat generated from the motor as it executes different tasks is also included in the model. And having this multi-domain, not only I can see the robot executing different tasks, I can also see what is the rate of depletion of the battery as it goes through different tasks, and also what is the temperature change in different joints. And this is an example to show the concept. So this is a lot more than just having to a multibody. There's a system level model that gives you a lot more by incorporating multi-domain components in your system. This is another model that I'm going to talk about. This is an excavator model, and here we have multiple revolute joints that provide the degrees of freedom that the excavator has. There are hydraulic actuation between different parts, and these hydraulic actuations are all bundled into the one subsystem to the left with the designation H. And we have translational domain that bring the forces generated by the hydraulics to each of the cylinders or where they are used. So we have multibody, we have 1D translational, and we have hydraulic components in one system. Of course, there are signals and 1D rotational in this system as well. Let's have a look at the playback of animation of this system, which incorporates hydraulic, as I said, and again follows a predefined path, which you can imagine as a captured command by the driver as it executes an operation, and then that was recreated with MapleSim. If we look at the hydraulic component, there are hydraulics. If you look at the hydraulic subsystem, you can see hydraulic components in it. We have a pump and circuitry and valves that actuate each of the hydraulic cylinders that provide the force to the appropriate places. So in this subsystem, we have, of course, hydraulics. We have signals because the commands for the predefined commands for the valves are captured in the signal blocks. And we have translational domain to bring the forces in 1D domain to the cylinders, and in one of the actuations are done through hydraulic motor, and that is carried through 1D rotational domain. This is another example, an industrial robot, which of course it has the multi-body components. We see subsystems that are connected through series of revolute joints. We have an inverse kinematic block that was calculated or generated by automatically generating the equation from the system and using Maple to solve them to get the inverse kinematics in a seamless way. There are electrical components for the servo motors, and the results of or the force or the torque exerted by the servo motors are carried through 1D rotational components. Let's have a look at the animation playback for this for a simulation, as through the path specified in this signal block, which traces the word maple in space. This goes through the inverse kinematic block, which converts the position of the end effector to the value of the first 3 joints. The 2 last joints were locked in place, and the motion is exerted through servo motors. So there are 3 servo motors in this component for the 3 active joints, and inside each of them there is an electrical motor and a gear reducer. A hybrid electric vehicle is another example that I mentioned here. So the actual vehicle is a full multi-body vehicle model with chassis, suspension, parts. This gets activated through a drive shaft that goes through the drive line or 1D rotational components. These gets energized by electric motors. So there's a pair of motor generators in this hybrid electric vehicle. There are more components in electrical domain for the battery or different types of inverters. And there's a signal for the driver commands. And there's a mean value engine component, which is done through signal operations. So that also can come online to provide additional torque or charge the battery. So looking just at the multi-body part of the model, we see the prismatic joints that represent the suspension, revolute joints that provide the degree of freedom for the tires to rotate, and we see 1D rotational components that bring the torque created by the drive, the powertrain, to the rear wheels. So these were the examples that I wanted to show in this webinar, in the hope that it will give you some idea of what are the different options or what are the different possibilities that exist in bringing a system level model that incorporates multiple domains into one environment and gain from having them all simulating together as gaining better understanding of the system. As I mentioned, there's a lot more to this, and we have a ton of material on our website as well for focusing on different aspects of what you can do with MapleSim. This was really a overview of the kind of models that one could create, and the possibilities of endless. So what lays behind beyond the modeling is stuff that you can do with your model once you have them in Maple and MapleSim. You can generate equations. You can, as you will see very briefly, manipulate those equations, do inverse kinematics from those equations, that constraint equation that you generate, go beyond inverse kinematic and do inverse dynamics, custom components that you can incorporate in your model, such as a special nonlinear spring that you want to add. Speaking of nonlinearity, you can use the equations of the system to symbolically differentiate them and create a linearized version of that system. Use that linearized representation in a state space form, transfer function form. Use it in dynamic system analysis, PID tuning, get the natural frequency of the system. These are all post your modeling and simulation activities. You can do sensitivity analysis. If you have the nonlinear equations, you can do nonlinear control, like feedback linearization approaches or other nonlinear control approaches. You can do parameter identification by using Maple's optimization routines to match the behavior of the system by varying the parameters to a given expected behavior, and thus identifying the system parameters. Variety of optimization techniques based on the parameterized equation of your system is at your disposal. Code generation is one of the things that you can do with models in here. Both multi-body or multi-domain systems, you can create code, you can get a C code or export it as an S function or an FMU or many other platforms. You can incorporate the model that you create in MapleSim in those tools as well. And of course, you can use Maple to create a design tool based on your system level model. So this is what comes after modeling and simulation, and I hope what you have heard today gives you enough of a reason to look into these other possibilities. And for that, one of the places, aside from sending us your direct question, is to visit our website, and there are a ton of material there to get you more answers into your inquiries about other functionalities of Maple and MapleSim.